There we go. I will get started. I think it's time. Yeah, it's been time. So let me work another example of areas bounded by curves. I've got some. So you see these? So these, like, this is the other way we could give problems, something like that, where I give you, like the graph and the shaded, and then, as opposed to like the ones we've worked so far, I've just given formulas, and then we kind of like find our way to what the graph looks like, and then interpret it.
So like this, we need to.
It could.
We need to graph the graphs.
Yes. It could go either way. I haven't really said. There might be one of each. Let's see here. So I'll work some of these here. Here we go. We've got a picture. So we're supposed to find the area bounded. It shades the picture like this here for us. All right. And it tells us that the formula is y is equal to x cubed minus 9x. We're supposed to find the area bounded as pictured. All right. Okay, so this one's pretty easy, I think. So like, where are these points of intersection? See, well, this is, we can factor this, right? This is x times x squared minus 9, right? Which is x times x plus 3 times x minus 3. So, if this graph was, if they continued the picture, we'd see that this has x-intercepts where? At like 0, right? Of course, here's the 3. But there's also an x-intercept back at minus 3 that's not pictured, and we don't care about that, right? Exactly, not relevant. So then the question is, do you want to draw a vertical, or do you want to draw a horizontal approximating rectangles for this one?
So here it's that way, right?
Yeah, vertical, that way, exactly. That's a good choice. So then the question is, if we do it like that, so of course the thickness is going to be a little change in x, and dA should be the top y minus the bottom y times dx. The top y, well, this case, the top y is just 0, because that's the formula for the x-axis, right? Like y equals to 0 is the x-axis. That's what's the top, and the base is given by the other formula, which was x cubed minus 9x. Notice that minus distributes. So we've got ourselves 9x minus x cubed dx. And that is for 0 less than or equal to x less than or equal to 3. So, man, I wish, see, this problem would have been a great first problem for us to do. In retrospect, like if I could have done this problem to start with, it would have been, well, I have mixed feelings. Like the 0 is kind of weird. We've had other examples where that wasn't 0, and that's been important. So, but this is a good example. Anyway, a is the integral dA, which here means the integral from 0 to 3 of 9x minus x cubed dx. So we integrate, right? What's the integral of 9x? 4.5x squared, yeah. So 9 halves x squared, and then minus 1/4, right? X to the 4th. Evaluate from 0 to 3. So the 0 does nothing, right? If you plug 0 into x squared and x to the 4th, you get 0. So we only need to like focus on the upper bound. So we get 9 halves of 3 squared minus 1/4 of 3 to the 4th power. So that 3 squared is 9. 9 times 9 is 81. So we got 81 over 2. And 3 to the 4th is also 81. That's 81 over 4. And so the answer, 81 over 4. because like a half minus a quarter is a quarter. So. See, 3 times 3 is 9. 9 times 9 is 81. You know?
Yeah.
And so half minus a quarter is a quarter, so. Which, for what it's worth, is 20.25, right? Like, if you're an engineer, that's probably a better answer, isn't it?
Probably.
But us, us math people, we like fractions. And us higher math people don't care about improper fractions, right? Like elementary school people would be like, no, 81 over 4 is wrong. You should say it's 20 and 1/4. You know, I think this. I told you before. I think this notation is very poor.
Yeah.
Because if we take 20 times 1/4, well, it looks like it's 20 times 1/4, right?
18.
So if you multiply this by 4, you can cancel the 4s and you can get that it's 20. Right? But that's not true, because what 20 and 1/4 actually means is 20 plus 1/4, right? So when you multiply it by 20, you get 400 plus 20 over 4, which is of course 5. So and of course these are not equal, right? this is a bad notation. But anyway,
I have one question.
sure. I digress, obviously.
What is dx in a graph? Like I top, y top, and y base. How do you get those numbers from
So
the
sure.
the pattern?
So this is y top is equal to 0, because that's the x-axis, right?
Okay.
But the y base is the cubic function. That's the one that's beneath it, right? And
Yeah.
so, looking for another color. Oh, whoa. So that one, check my mic. Okay, still working. So that one goes down here, right?
Yeah.
So that's the base y, and so dA should be the this, whatever that distance is. Let me put it in here, h, right? It should be h times the width of that strip. So I'm imagining it's just a little change in x, so I use dx to denote that. Now, so okay, fine. Maybe I should do it once. I'll do it once. You could say, okay, so I'm going to partition 0 to 3. Partition to n boxes, And so I've got, 3 minus 0 over n is my delta x, right? And I could say my x sub I is I times delta x, which is 3i over n. And so my little bit of area would be, y top of xi minus y base of xi times delta x. And to find the whole area, I take the limit as n goes to infinity of the sum. So this is the ith delta A of these guys. So that's, let's see here, y top of xi, that's 0. Y base is, I'll just write it this way. 9xi minus xi cubed delta x, So this would be, instead of thinking of dx, actually thinking of, a little, actually finite increment delta x at, x sub I. So this would have area delta AI, and then you add those all together, take the sum I equals 1 to n to get the approximation of the area. Take the limit as n goes to infinity, that gives us the actual area. But what happens when you look at this, when you actually look at this is nothing more than the Riemann sum of this. So rather than, rather than writing down this kind of stuff and setting up the finite sum to describe the area, and then saying, oh, well, the limit as n goes to infinity, that becomes the integral, I just get straight, I use a mnemonic, sort of a, what's the word? A notation which is a shorthand for this entire box of thinking. And I instead just say, well, it's like a little dx. And in so doing, I avoid discussion of the limit as n goes to infinity and switching to the Riemann sum. I take the intuitive perspective that if I relate the infinitesimal area of this strip to the infinitesimal change in x related to that, then I can integrate this equation to get the total change in A as it relates to adding up these things. So that's a philosophical idea. This is the infinitesimal method. Again, it's really just a shorthand for not going through all this for every one of these examples. See, I have never written down any of this stuff before this point, and I think you see why, right? Because it takes time. I don't think it really adds much for most students, and I think it confuses more students than it helps. And it is a bit of an abuse in some sense to use dx like this, but from another perspective, it's not, because you can actually build calculus with what's called the extended real line. You can actually take real numbers and adjoin to them numbers which are like very, very, very small but not zero, such that the reciprocal of those numbers is infinity. And you can, through formal algebraic means, construct calculus without limits. So you can replace limits with what we would call abstract algebra. Now that's not what's commonly done, but there is a firm, rigorous logical setting for thinking of dx as actually being like a really, really tiny number. And that is what the founders of calculus thought about derivatives. They really did think about dy dx as being a notation for talking about like a little bit of y divided by a little bit of x. Now, that was not how we defined it, right? We defined it in terms of like the slope of a tangent line, but you can also think of it in that way. And in view of that, this is not such an abuse. Anyway, I digress. As you can tell, what I'm talking about is more philosophy than mathematics, isn't it? Yeah. Let's do another. Unless you got questions about homework.
I think one was to use substitution, right?
Which mission are we talking about?
Maybe it was 8.
Mission 8.
Yeah.
No, you said mission 8 could be use substitution, but
119.
problem 119. Let's see here. I will take. Let me do one more of these, and then I'll get into that for you. And so this is y equals x squared. And again, we're given the picture. The ones we're looking at today, we're given the picture. Makes our life a little bit easier, doesn't it? And so this one's y equals to, where did it go? 12 minus 2x squared. And we're asked to calculate the area, which I'm about to shade. So like this area. So for that, I would point out that the This is actually, despite the fact that I wrote this, notice I wrote this label up here, but if you follow it back, if we do our rectangles like this again, which I think we should, right?
Yeah.
If we do it like that again, this is the base, isn't it? And the other one, actually, see, follow it? It's the top. It's just that they cross here and switch their roles between, you know. And so dA is going to be 12 minus 2x squared minus x squared dx, right? Which, of course, we could simplify a little bit, right? dA is actually 12 minus 3x squared dx. So what's left for us to do before we can solve this problem? We need to figure out what? I mean, I can't integrate. So these kind of problems, the answer is always a number, right?
Yeah.
So we need to figure out integrate over what, right? This picture makes sense from, I mean, you can see it in the picture, right? From this point to that point, right? So what are those? Right, we don't know for this one yet, do we? The points of intersection?
Put them equal to each other.
Uh-huh, very good. So we put x squared equal to 12 minus 2x squared. What's that give us? I think, so this one I can, if I had 2x squared, I get 3x squared equals to 12, right? Which gives me x squared equals to 4. So what happens when you take the square root of that equation?
2 and minus 2.
Yeah, 2 and minus 2. So that says x is equal to plus or minus the square root of 4, which is plus or minus 2. So there you have it. We can then calculate the area, right? We just need to integrate. So area is the integral from minus 2 to 2 of 12 minus 3x squared dx. Can you think of anything to make our life easier here?
Divide by 3.
Divide by 3? Oh, that's true. I mean, the integral will have a division by 3, so the 3's cancel. That's true. Good. But how about this? Is there anything we can do before we even integrate, just based on this, like, symmetries of this problem? So, like, look at this. Is this an even function? Is it an odd function? Because we're integrating from minus 2 to 2, right? So if it's an odd function, it's 0.
Oh, yeah, we can from 2 to 0 times 2.
Mm-hmm. Very good. So we just double the integral from 0 to 2 is the easier way to do this. I mean, that'll save us some arithmetic. You know, it's a worthwhile. If you can do that, do it. I mean, it saves you annoying arithmetic. And so then integrate, right? What do we got? We've got 2 times 12x minus x cubed, I believe. Because the 3 and the 1/3 cancel, right? The 3 and the 1/3 cancel. So what's that? That's 2 times 24 minus 8. Notice that the 0 gives us nothing. Oh, there's fruit flies in this building. So annoying. The 0, of course, gives us nothing, right, when we plug it in. Don't always, just because it's 0 doesn't mean it's automatically nothing. there are integrals where even though the lower bound is 0, you get something from it, like if it's kind of exponential, or the cosine is the antiderivative. So, but this is x. When I plug 0 into that, nothing, right? 24 minus 8 is 16 times 2, 32. So there you go. Yeah, not too bad. So these problems are pretty friendly. All right, so let's spend the rest of our time looking at your homework, if you don't mind. So which problem are you troubled by? From 109, did you say?
Yeah, 119.
Oh, 119. I'll have to look at what that problem was.
Yeah, I don't have it here.
You don't have it here? Okay.
No.
Now, just a second. I will load it up.
Screen up on my computer.
It's okay. I just got to log on here.
Well, I have the program actually, but I don't have every problem. So this is 119.
So 0 to pi of cosine of x over 2. Okay, so what did you try?
Try to use substitution.
And would you let u equal what?
X over 2.
Very good. So then du is what? 1/2 dx, which means dx is 2 du, right? So we get what? Cosine of u times 2 du. You got that much? Did you get that?
Yeah.
Okay. And then we have to change the bounds as well, right? So u of 0 is 0 over 2, which is 0. U of pi is pi over 2. So we, in the u, our bounds are 0 to pi over 2. Unless I made a mistake. Oh, no. So once you have that, you should be able to do it, right? Like, what's the integral of twice cosine? It's what? 2 times the sine of u, isn't it? And I've got to evaluate it from 0 to pi over 2, right? Does that make sense?
Yeah.
Okay. And then evaluate. So we got 2 sine of pi over 2 minus 2 times the sine of 0. Of course, sine of 0 is 0. Sine of pi over 2 is 1. So we get 2. I don't know why, but it feels wrong. Oh, never mind me. I realized, I know what's wrong about my thinking. The reason I was concerned. I won't try to explain it to you because it was wrong. So let me not invite you into my confusion. So there we go, 2, apparently. What other one were you stuck on? Let's see if my computer is.
I don't have enough here.
Yeah. Oh, well, there's signs of life over here. We'll see if I can. Come on. Let me in. They really don't have it set so your profile follows you around. Every time you use a new computer, it always kind of, you go back to square one. All right, Calculus 1. And where are we? Mission 8, was it?
Yeah.
So which,
Mine is due to tomorrow, right?
yep, that is true. Let's see here, so, oh, the dog problem. The rate at which dogs bark in a given apartment is dBdt is 10 sine pi t over 4.
Yeah.
Uh-huh.
1 to 1.
121. Okay, sure. We
I
can
think
talk.
I sold this one, but I'm not sure.
So you're stuck on this problem 121.
Yeah.
Okay. Yeah, we can talk about that one. So remember the net change theorem? Net change theorem says the change in y is equal to the integral of like dy dt dt, say from t1 to t2. This gives you the here delta y would be like y of t2 minus y of t1. So that would be the net change in y. Now, I think I wrote the theorem before in terms of x and y, but maybe it's good to write it in terms of time. Excuse me. My apology to the people on the YouTube. That might have been deafening, I don't know. So I asked you to calculate, the net number of barks during a certain time period, right? Yeah. And I give you the infinitesimal rate of barking, okay, in this problem. I say that the rate at which dogs bark is given by dB dt is 10 sine of pi t over 4. Right? And I say to, basically, the question is calculate the number of barks, which you could say is the change in the total number of barks forever and ever from time 0 to time 2. So what we got to do is use the net change theorem, right? We just say, okay, so like the number of barks we're looking for, it should be the integral from 0 to 2 of dB dt, right? But in this case, we're also given the formula for dB dt, right? So we can do that integral. So we just have to integrate from 0 to 2 10 sine of pi t over 4, right? So what do you, can you do this integral? What do you think? It's a lot like problem 119, actually.
Yeah.
What would you let u equal to in this one?
How is the U substitution?
Uh-huh, you could do that. You could have, I think you could also have guessed, you could have guessed that 2 times the sine of x over 2 is the antiderivative of that. Like that is something you could have guessed, right? If you'd been in the mood for guessing, I think that's definitely something you could have done. That was the spirit in which this problem was originally assigned, because this problem set didn't assume U substitution. So like, in the same way, I could tell you that the antiderivative of this is, 4 over pi times 10 minus cosine of the same thing. But let's do the U substitution, like you said. So U equals, yeah, I think it's not a bad idea. So pi t over 4, right? So how are du and dt related? Well, we got du is pi over 4 dt, which tells me dt is 4 over pi du. We also need to change the bounds, right? Well, zero doesn't. Zero stays the same, doesn't it? Like u of 0 is pi times 0 over 4, which is still 0. But u of 2 is pi times 2 over 4, which is otherwise known as pi over 2. So when we change the variables, we get integral from 0 to pi over 2 of 10 sine of u times 4 over pi du. So that's my u substitution, right? Change the integrand, change the measure, change the bounds. See what I did? So I just, this dt becomes these two guys, right?
Yeah.
10 is 10, the sine of u, and then of course 0 became 0 and 2 went to pi over 2. So can you integrate that? Well, what, like minus 40 over pi, right? Cosine of u? Agree? Disagree? What do you think?
Well, I guess so, but I don't know how.
Well, what's the integral of sine?
Cos.
Right. So that's really all I'm doing is the integral of sine of u du is minus cosine of u plus a constant, generally speaking. But,
Yeah, but how do we get minus 40 over pi?
well, there's, I'm sorry. So 10 times 4 is 40. And then, so I just multiply these numbers.
Okay.
That's all, yeah. Oh, I got you. I'm sorry, I didn't think about that.
Those numbers doesn't change at all, really.
No, they're just, we get the minus from the integration, but the 10 and the 4 are just multiply to give us 40 and still divided by pi. So,
Okay.
like the algebra step there is if we have a times b over c, that's equal to a times b over c. That's the, that's the arithmetic rule I'm using. So then we can, and of course I'm using fundamental theorem of calculus part 2 as usual, right? So we got what? We got minus 40 over pi cosine of pi over 2 minus 40 over pi cosine of 0. What's cosine of pi over 2? What's cosine of 0?
Is that 1?
Yeah, cosine of 0 is 1. Very good. And cosine of pi over 2 is just is 0, right? Cosine of 90 degrees, if you like. So cosine of pi over 2 is 0. And so minus minus gives me plus, and the answer is 40 over pi. So your major is like financial math, right? So like, can you have 40 over pi barks? No, you can't, right? So to give a more realistic answer, you actually need to find the decimal form of that and say, so they're about, whatever that is. So 13, about 13 or so barks. 3 times 13 is 39, but it's got the 0.141, blah, 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 blah.
Yeah.
Ballparkish. But anyway, this is a very silly problem anyway, because how on earth would you know that like the density of barks is given by a sinusoid? It's like, and also this formula is very questionable. Like, you start thinking about it more, I'm saying sometimes there's a negative. Like there's, well, I guess you could have a decreasing number of barks per time, but if you had dBT was negative, you could somehow undo a bark actually with this formula. You could have negative barks. I don't know what that means. What's a negative bark? I mean, I suppose only really Fauci could answer that, but. So, all right. That was a joke about the recent thing that's come to light in terms of the abuse of puppies by the research funded by our government. So, which has led to the People for Ethical Treatments asking for the resignation of the Fauci. I don't know. The world is strange. So did you also have questions about the last one? Or was it mostly that one, like problem 122?
Yeah.
Now problem 122 is an area bounding problem.
Can I include this in what I handed in to you?
Yeah. You're welcome to.
Again?
Yes, you're welcome to use my solution, of course. I mean, you asked.
Okay.
The important point is that you learn how to do this. So if you learn with me or you learn when I'm not here, either way is fine with me, as long as you learn,
Yeah.
So the next one, this was problem 121, wasn't it?
Yeah, this was.
So problem 122, you had y equals x cubed, and you had minus 2 less than or equal to x less than or equal to 2, and you're supposed to calculate the, well, you're supposed to find the area bounded by y equals x cubed from minus 2 to 2. And I think my language is, I should probably say area bounded by curve and x-axis, just to be, I mean, you could complain my current instructions are ambiguous because there really isn't an area bounded by y equals x cubed. So what I intend is the area between y equals x cubed and the x-axis, right? So y equals x cubed looks like what? It's the cubic, right? So it's one of these dudes. And I'm asking you to find this area. So I think you can do that, right?
Yeah.
Right. So I think this one you can do. I mean, one way to look at it is you can say, oh, well, that's just the integral from minus 2 to 2 of the absolute value of x cubed. You can look at it that way. Because the absolute value of x cubed, it just takes this thing and flips it upside down, right side up rather. Like absolute value of x cubed, it just turns this part of the graph up to here. But I think you can see from this, like, the easy way to do the calculation will be just to double the area from 0 to 2, right, by the symmetry. Yeah, so I'll let you do that one. I don't want to ruin it for you. I think, I was thinking about, so we have a test next Thursday, right? Which is the Thursday before Thanksgiving. So, we still have Tuesday and Wednesday to talk about homework and stuff, but I think it would be good for you guys, a healthy thing, if you took a quiz Tuesday that's like the test. So,
Is it graded?
yeah, a graded quiz Tuesday, but I guess it's bonus because I think I've already allotted all the points for the course, if I'm not wrong. I think if you look in the
Because the last test now, next week,
So-
it's only about integral streaming, right? And area graphs and stuff.
yeah,
Not much else.
right. So let's see here. Yeah, like at the moment, I think I have everything in the Grade Center listed. I have like the final exam, test 1, test 2, test 3, note-taking, participation, all your missions, even the antiderivative worksheet, all that stuff. And there are 1,038 total points. All right. So my grading system was based on 1,000-point scale. So remember, 900 and above is an A. So there's already like 38 extra points. But I'd probably make this quiz worth 10 points. So if you did perfect on it, you get 10 points. Great. But the larger point of the quiz Tuesday is you'll have a time pressure chance to find out what you don't know. And then I will grade it and give it back to you guys Wednesday if all goes as planned.
1,000 points.
What's that?
1,000 points in total.
Yeah.
Sounds very much.
Well, it's just, other people use percentages. This is how my previous institution forced me to do it, and I'm just a creature of habit at this point. I used to have 10,000 points. That was even better. 10 times better, really. But that one is kind of intimidating because then you have a test that's worth like 1,500 points. So I don't know. The point is to learn anyway, so as long as we're doing that, we're in the right place. Do you have any questions about Mission 9? Because you could ask me about that. I think we still have some time.
I haven't started on that one yet.
You haven't started on that one yet? All right, well, I guess we'll stop here for now then. We can talk about Mission 9 tomorrow.